And I've put here, there may be several correct ways to analyse an experiment. Now the reason I put that is, when I was writing this, I thought back to my early days in cytometry, and the postdoc in the lab who taught me how to operate the machine, or buttons to press really. And I remember showing him my analysis, which was relatively basic actually at the time. I showed him my analysis, oh no, you don't do it like that, you do it like this and this. And thinking back, I now realise that actually what he meant was, no, that's not the way I'd do it. I'd do it this way. It's not the same thing. So I've always taken the approach that if someone says to me, oh, I'm analysing my data, is this right? If I look at it and it's not the way I'd do it, but it's correct, I will say, yep, that's fine. I might do things a little bit different. And if they say, well, how would you do it? I'd say, well, this is my approach, but my advantage is this, but then it has the disadvantage of this and this and this. I would never say to someone, no, you've done it wrong, simply because it's not the way I do it. And often you can do 2 or 3 different gating strategies and you end up with the same data. Okay? It's whether it's correct that's important, not which way you do it. And try and keep it simple. I mean, I know that's, a good maxim in anything really, especially in science, but the simpler you keep it, the better and probably more robust your data will be. If you overcomplicate things, you end up with problems. So in terms of analysis software, there's a lot out there. This is by no means comprehensive, by no means. Flojo is the most common, one of the most common. It's by far the most powerful, but it's also got a very, very steep learning curve and is horrendously expensive. Kaluza is unbelievably expensive because they didn't listen to me when they first released it. I said sell it for 1,000, I'll sell you hundreds and hundreds of copies a year, and they said no and sold it at 20,000, so they didn't sell any. Now they've brought it down to 5,000, and they still don't sell any because people are not going to pay that. And what they do is they use it as leverage when they buy instruments. So if you say to Beckman, I'm interested in Cytoplex, they say, oh, we'll throw 4 copies of Kaluza, that's £20,000 worth. You save 20 grand. Sort of, you could buy an equivalent better software for £1,000, but that's one of their business things. FCS Express is very good. WinMDI still works on Windows 10. Now, it was originally written for Windows 3.1. Does anyone know Windows 3.1? Yeah? Not many nods. Not really very surprising. It was the one before Windows 98. So you not Windows 95. Yeah. So do the maths on that. Well, the trouble is, I got laughed at on one course because I pointed out I didn't have an email address as an undergraduate because there wasn't a university email system. Well, not for students anyway. I got one when I was a master's student, and then the World Wide Web came online, which was quite good. So that does make me feel old, it really does. What was that, 95, I think it was. So, yeah, terrible. SIFLogic is a free one. But every time I've installed it, I've uninstalled it within half an hour or so. So that probably says a lot about that. There's another couple, they're very, very strange, these ones. But then of course you've got all the ones that run the instruments. So the Acuria has its own one. The BD machines have Diva software, which is a Diva. It works when it wants to work, and it doesn't when it doesn't, and it does very strange things just because. Whenever I run hands-on courses on Diva instruments, I spend at least 40% of my time shouting at the software. So it's not doing what I want it to do for whatever reason. Does anyone use Diva software? Anyone really enjoy using the Diva software? No, I didn't think so. So basically there's a load of different softwares, but when it comes down to it, they all operate the same way. So much so that I was asked to go and do some hands-on training for an instrument I'd never used before, on a software I'd never used before. And I couldn't even find a manual. But when I got there, they said, I'll have a play around with it for half an hour while we gather all the trainees, and then I ran a training course. And everyone said, that was brilliant, thanks, I really know how to use it now. And I didn't say I've never used it before this morning, but because I've used all of these softwares over so many years, they're all the same at heart. They've all got the same principles. Really, it comes down to what menu things are on and what order you load things up in, and whether do you right click or choose this. That's what a lot of it comes down to. So I'm not going to go over data files again, but in terms of acquiring events, how many do you need for statistical significance? How many do people tend to acquire? 5,000 anyone? 10,000? Yeah? More? Anyone acquire big files? What sort of numbers? 100,000? 500? That sort of thing? Yeah? Well, sometimes you have to. So this figure was put together by Amnis for the image stream, but it holds true for standard cytometry as well. So what they did was they took two different samples with different fluorescences. So, and the relative difference between them should be 3. Okay? So if you run 10,000 of them, the relative difference between the two populations will be 3. But first of all, they ran 10 and 10, and they repeated that 50 times. And so what they did was they worked out the relative difference between 10 of them and another 10 of the other population, repeat that 50 times and plotted them here. And as you can see, 10 and 10 gives you anywhere between about 0.5 and 6. Okay? That's not great. You don't want to run 10 of each. By the time you get up to 50, we're somewhere between 2 and 4. That's still pretty awful. 500, 2.5, 3.5. 1,000, 2.7 and 3.3. A lot closer. Not perfect, but a lot closer. But then look how much it improves between there and there. 2.8, 3.2 maybe? Improves slightly. Between 4,000 and 10,000, I'm sure it doesn't really change at all, that figure. Above 10,000, no real change. So what this is a good guide to is, how many cells do you need for statistical significance? And really, above that line, you're pretty much there. But what you've got to remember is your cells of interest. It's not total cells. If you acquire 10,000 events, but there's only 200 of your cells of interest, you're down in this region. Okay? Now, I mentioned earlier that person who runs their sorter all day and ends up with 100, 200 events. They have no choice. They're running hundreds and hundreds and hundreds of millions of events all day, and still their sample of interest is down here. They have no choice. It's not ideal, not optimal. I wouldn't say statistical significance was very high, but there is nothing else they can do about it. So, by and large, you need to be above this line. So people say, well, why don't I just acquire 1,000 cells then? Why am I acquiring 10,000? Well, of course, once you get rid of debris, and doublets and aggregates and bits and pieces you don't need, if you only acquire 1,000, you're suddenly down here somewhere. It's not so good. And say, oh, all right, 2,000 then, because even if we lose half, it's still down. Yeah. The other thing, of course, you've got to consider is that the instrument operates at anything up to 10,000 per second, most of the BD instruments. Some of them are faster. If you put a relatively concentrated sample on, this is 1/10 of a second. 10,000 is 1 second. How long has it taken you to label those cells and prepare those cells? How long has it taken to get that sample to the labelling stage? A week's work? And so you might save yourself half a second per tube. Even if you've got 30 tubes, that's 15 seconds. To be honest, if you sneeze, you can waste more time than that when you're running the instrument. So, you don't save much by only acquiring 1,000 as against 10. Now, admittedly, if you've got a very, very dilute sample, where it's running at 12 per second, yes, it's going to take a while to get to 10,000. You might want to stop earlier. If you're just having a quick look, if you're doing compensation samples, yeah, fine, this area's fine. But where this figure really comes in handy is if you're looking at a subpopulation within the main one. If you acquire 10,000 and your cells of interest are 2% of that, yeah, you're back down here somewhere. So keep this handy and refer to this if you are looking at much smaller populations. Okay. So graphical plots. Histograms, dot plots, they're the standard way of looking at things. Contour and density plots really are used when you've got an awful lot of cells. Because if you look at this one as a dot plot, basically that's full. You can't see anything, it's just full. Now, one way of showing that as a dot plot and still showing there's a lot here would be to only show 10% of the events. Most software will let you show only some of the cells. And what it will do is it will just not do 9 of them, in the list, then it'll do the 10th, then it'll not do the next 9, then the 10th, so it randomly selects them, which means you should, in theory, end up with a black blob here, a greyish bit here, and this will be sparse dots. If you do 10% or 1% or whatever it might be. But contour plots can be useful as well. 3D plots, now for some reason the Flowjar on my laptop will not do 3D plots, the button isn't there. It's there on my PC and I installed it from the same file, but it's not there on the laptop. Don't know why. Mind you, on the laptop I can show groups on the layout editor. I can't on the PC, button's not there. That's Flowjar for you. It's a bit like the Diva software in that respect. It just likes to be awkward. You know, it doesn't like being helpful. So 3D plots, I can't show you, but they're great if you can get them rotating and you can show populations appearing, disappearing, and so on. If you're doing a presentation, doing a conference talk, anything like that, fantastic. Use 3D plots, they're brilliant. If you're going to put them flat on the page, don't. Because that's like one of those weird sort of optical illusions. If you look at it, is the blue point at the back or at the front? If you stare at it hard enough, it sort of seems to flip backwards and forwards. Or mine does anyway. My brain does. It's very, very hard to read a 3D plot flat on the page. So I wouldn't ever put them flat on the page, but if you can get them animating, they're brilliant. Then we've got this radial plot. So this is in the Kaluza software. And this was an attempt to deal with the problem of modern multicolour cytometry. So one of the issues with cytometry these days is, how do you analyse data from, say, a 13 colour assay? It's fine if you know that you've got a gate on these and these, and you want that, and these and these, and you want that, and so on. It's fine, you've got a predetermined gating strategy, fine. What if you haven't got one? How do you analyse 13-dimensional data? If you printed out all of your possible plots, you know, we would fill that bit of the floor there with plots. That's not particularly helpful, because you can't look at all of those and analyse them. So what they're attempting to do with this radial plot is, here they've put on 4 different axes. You can actually put on up to 12. The idea being that if we then take this and move it, any dots that move are CD4 positive. And the more they move, the more CD4 positive they are. And you can actually get those animating and just rotating around at various speeds and things. The idea being that you can put 12 different parameters on, and then move the axes around and see what populations appear, and then you can gate on those and so on. The problem is, you're actually asking the scientists then to analyse 12-dimensional data on one plot. It's a bit of a gimmick in a way. I can see where it might be useful in some circumstances, but I can't see anybody seriously using it for that. And no, I know quite a few people who have Kaluza, and none of them use it. Not in any serious way. Mind you, it's a bit better than Flowjar's attempt at multi-dimensional data analysis. I'll very quickly show you this because this always makes me laugh. People could probably do with a laugh. So, drag plate statistics there, and so. Right, geometric mean equals that. So, so the way Flowjar tries to deal with multi-dimensional data analysis is to essentially do. Oh, why isn't it done a heat map? No, well ID.
Is this the deep part you're on about?
Hmm?
Is this the deep part you're about?
Yeah, this is quite intriguing. As I say, I ran one of these yesterday, and it as I say, it did get quite a laugh from people. Oh, I know why I didn't do it, because there's no data. Right. So multi-dimensional analysis is quite important. You know, how do you look at lots of data? Let's just put in a statistic. Doesn't matter what the statistic is I'm adding. Right, so it does heat maps, is one way of doing it. So a heat map, this is showing the forward scatter median for each of these 8 populations. And it will actually allow you to do two-way heat maps where you can put another parameter in, and you can have one parameter top left and another parameter bottom right. And the colour tells you how much of it there is. But that's only 2-dimensional data, but for a big plate. If you want to do more than 2-dimensional, you have to go to this. Okay? These are called Chernoff faces. So what I'm going to do, I'm going to put the amount of forward scatter as, where should we go? Should we go for Grin? This one's really happy, he's got a high forward scatter median. This one's not so happy because this is quite low. It's been a long day, it's been a long 2 days. Okay, the idea being that you can choose one of these. So we could go, if we go for, I don't know, a statistic, and we add side scatter median, put that up there, with samples, drag that on there. There we go, side scatter median.
Has it appeared in Nature or Science yet? Is that
No, strangely enough, it hasn't, and I'm not quite certain why. You know, so this one's quite shocked. He's got loads of side scatter, and this one's not particularly impressed with his side scatter. So yeah, all right, it's, you know, it's a laugh, and I put it up just to lighten the mood a little bit. But this is an attempt to display multi-dimensional data, and if you see how many different parameters there are, we could do 10-dimensional data using this for a 96-well plate. We could show 960 parameters, essentially, in one figure. The downside to this is, you know, the grin is okay. A grin means a lot, a flat mouth means none, the eye size are big eyes. But when you get to like head shape, is this a lot or is this a lot? I don't know. You know, and you'd have to calibrate it. And does this one have more than this one, or does this one have more? It's a bit hard to tell, you know. And then you go for one of the more even esoteric ones, like the nose size. Can you really tell much from the nose on that? So,
how do you put error bars on it?
See, now that's the trick. I don't know, maybe it draws a little hat, and the bigger the hat, the bigger, I don't know. You could probably doodle moustaches on it or something, couldn't you, to show error bars? And a big moustache is a big error bar, and a small, I don't know. But the idea behind this is, you want to be able to show multiple parameters in one format. And so Kaluza has the radial plots, this has Chernoff faces. Some have sort of branching trees that show percentages in different parts. They've all got their own approaches, and none of them really have cracked it. How do you show 13-dimensional data? I don't know. So yeah, have a play around with that if you ever want to on FlowJet. It's quite fun. And so every plot has its own bonus and drawback. Right, so bi-exponential plots. Bi-exponential plots are a pain in the backside. So bi-exponential is where you show data below the axis. So you'll often have seen plots that look like this, yeah, where your data is heaped up on the axis. The reason is we've got negative values on a logarithmic scale. So at this point, mathematicians sort of start to quiver a bit, you know, and their eye starts to twitch because they can't quite handle this concept of negative values in logs. Now, of course, we're cytometrists, we're special, we can have those. And the reason is actually the same reason we get the fishtail. We apply compensation to data that's already been applied to a log scale. So it's been put on a log scale. And then we're taking off values, but we might be taking off more than we need to because of the data variability. So it ends up below the scale. So we end up with this. So what does it look like below that? So what you do on a bi-exponential scale is you add negative values to your scales. Because the software knows what the value is, the real value is, so you get a proper bi-exponential scale. Now, that's not what I have an issue with. What I have an issue with is how the software deals with these. And I'll show you that in, if we look at that, and I'll just quickly gate that. So this is Flojo, okay? And if we look at fluorescence on Flojo, fit C versus PE, okay, for A1. This is a bi-exponential scale. 10 to the 5, 10 to the 4, 10 to the 3, 0, minus 10 to the 3. So that little bit there is 10 to the 2 down to minus 10 to the 2. So not only is it applied a negative log, it has also applied data compression around 0. The Diva software doesn't do that. It doesn't do data compression, nor does it use negative logs. It uses negative linear, which is even worse for mathematicians. You've got a negative linear and a positive log. But the big issue comes if we then look at new sample. Let me just import the FCS file. Where is it? Desktop. Upload your data. Run. Okay, so we get the same forward and side scatter. That looks pretty similar. And then we do CD32 versus CD86. That is not a bi-exponential plot. When you open it in Flojo, it automatically brings up bi-exponential plot. Diva software doesn't, Nova Express doesn't. Okay? We can look at it as a bi-exponential plot. So that's now bi-exponential. That's also got compression around 0, but it does it in a slightly different way, because that is exactly the same data as that. Do they look the same? There are similarities, but at first glimpse, they don't look particularly similar, do they? The problem is the Diva software will look completely different again. And so if I'm working with, say, two of you on a collaborative project, and one of you is using Diva software on the machine, one of you is using Flojo, and I'm using this software, when you send it to me, I don't even open it like that, I open it like it was. And if I think, oh, actually, I better look at it by exponential, it still doesn't look like what you're looking at. But the two of you are looking at something different also. Now, in Flojo, we can go to straight log axis. And if we go back to log axis here, now, admittedly, that is a dot plot, so if I change the plot type and change it to, yeah? If I look at that and I look at that, they are the same file. I can see they're the same file. So I personally recommend, at least to begin with, look at data as a log on a log scale rather than by exponential. If only because the Diva software will show this when it acquires it. The Nova site will show this. If you convert Flojo to log, it will show the same thing. FCS Express will show the same thing. Kaluza will show the same thing. They will all show the same thing on log. But they will all show something different if you look by exponential. So I would recommend using logs to begin with until you're fully happy with what it will look like, okay? Let's go back to so it's by exponential. So gating. Often I get asked, where's the best place to put a gate? My answer is in the best place. Now, it's not very helpful. And if you say that to someone who is in the middle of writing up their thesis, for example, which is, I admit, quite a stressful time, haven't been there, done that twice, people do tend to throw things or swear, which is not great. But it is the only answer you can give. The best place to put a gate is in the best place. Of course, I can qualify that by saying, well, there is a way to work out the best place, and that is generally using experimental or biological controls. So, for example, here's my NK assay. NK cells, target cells. So that's my target cell gate. If I stood up at a conference and put this up, someone would say, why did you put the gate there? If I said, it looks about right, no one's going to give me any respect whatsoever. If I'm at a cytometry conference, I'm going to get laughed at. Because you can't put a gate, it looks about right. Now I do when I'm doing quick analysis, but that's years of experience. However, if I had a slide that said, well, when I ran target cells only, I got this, and when I ran NK cells only, I got this. So by putting that there, we got optimal differentiation between them. Now someone might say, oh yeah, but you ought to put it up there and do a 2% gate rather than 1%, because fine, that's just discussion, that's just interpretation. But at least I've said why I've done it. So this is my live dead. This is a live dead assay. Why have I put it here? Well, one I ran and I couldn't find the actual file and made the slide, had been treated with detergent, and the dead cells were there, and they were all within that marker region. So I put the marker region there because it just about enclosed the whole dead population, but it didn't include any live ones. This quadrant is quite easy to place. You can see where that population ends. You can see pretty much where that one is. That one's straight. Then you've got ones like this. What you've got to remember with gating is how tight do you want it to be? Well, it depends what you're analysing. That is relatively easy. This one, less so. Okay, if we're putting a gate here, we've got that side population. If I did a gate like that, okay, then I'm going to have more of my cells of interest. Because what you've got to remember is that this and this, because the populations are next to each other, they're not like that. Okay? It's not at this point, they stop being this type, cell type, and become that cell type. They don't. They're like that. So the further you move it that way, the less contaminants you get, but the less of your cells of interest you get. Okay? So if we tighten that in there, it gets purer and purer and purer, but we actually lose cells of interest. If we go the other way, we get more and more and more cells of interest, but we get more and more and more contaminants. You have to decide what you need. Is it absolute purity you need? Is it absolute recovery you need, as in the more cells of interest? It's got to be up to you to decide. So when you've got two very close populations, you need to know what you're looking at when you do your analysis, when you place your gate. But what you would then do is, in an ideal world, you would run some of this type of biological control, if you had one, or purified cells, or whatever. You'd run those and you'd put a gate on those. Because then if someone says, why did you put it there? You said, because. Here's my supplementary figure 1. Okay? So you need to put gates in a particular place because, again, this is my forward and side scatter. It's not going to make a great deal of difference to make that a bit bigger or a bit smaller. No real difference, to be honest. But you need to know that's what it is. So, if in doubt, gate on those ones and see what their profile is for fluorescence. Are they different to these ones? If they are, exclude them. If they're not, keep them. You need to sort of play around with your data. And that is more or less a technical term for me. Play around with your data. When you've acquired the data from your experiment, try things. Add gates, take gates away, move gates around, draw different plots, have a look, see what it looks like. That's the only way you will actually get to know your data and find sort of populations you maybe didn't even know you had. I'm not going to go for sequential gating, that's too obvious. And actually, I'm not going to do backgating. I'll include this one. Backgating is basically where you show a later population on an earlier plot. Flojo is supposed to do it, and it's rubbish. It doesn't work. So I sort of got out of the habit. Actually, let's very, very quickly do on here. So, let's close that down, and close that down. If, for example, we wanted to look at CD32, CD86, and we gated on that population there, and then we gated on CD209, CD14, and we gated on those there. Where are they going to come out on our forward and side scatter? Do we know? I'm got a clue. So what we would then do is we would then do the forward scatter one. Now, the green dots, which are primarily here, are these ones. Now, where this actually becomes useful is, say you're looking at quite a complicated mixed sample type, blood or something like that, or maybe bacteria. Because when you run bacteria, your bacteria are here and your debris is here. So how do you separate them out? What is your bacteria? Well, you use labelled bacteria and you do fluorescence first, gate on the fluorescent events, then plot those on the forward and side scatter. So it's sort of back to front. To be honest, people don't tend to use backgating very often. It's just about finding a specific population. Okay. Right, so stats, the other part of data analysis. So obviously we're using our plots to subdivide our populations, then we need our stats. So the bottom ones, well, the bottom ones here, are used to look at the amount of fluorescence. The top three are used to look at populations, number, percent total, percent gated. But say you're all my supervisors, interesting thought, okay, and I've run my experiments and I'm presenting you my data, and I said, right, so my project is to try and increase the number of T cells. Okay. Last week I ran my assay and I had 100 T cells. This week I've got 300 T cells. Have I done well? I can see a few concerned looks. Yes, no? Thumbs up, thumb down? Middle? Don't know. How many cells did I run? If last week I ran 10,000 and this week I ran 100,000, no, not really. I've done worse. So I go away and analyse it and come back to you and say, right, well, my T cells last week were 4% and this week they're 6%. Have I done well? Come on, you must know this by now. Yeah, depends. If I've got a lot more debris last week and no debris this week, no. Because if I've got, of that 100,000, if 80,000 is debris, no, that's terrible. So go away and reanalyze it and say, okay, right, fine. Of my lymphocytes, my T cells are now 40%, and last week they were 30%. Have I done well? Come on, you know the answer by now. Anyone? Word begins with a D?
Don't know.
Don't know, depends, yeah, exactly. Don't know. Because what if I've had a B cell depletion? My T cell percentage will go up, but I might have less actual T cells. Okay? So these numbers have got to be used with care. Now, sometimes you can use them straight off. If you've got a cell line and you treat it and you say, right, what percent are dead? You run them through, you gate on your cells, 12% are dead with this treatment, 80% are dead with this treatment. Yes, this treatment kills more. Because you've got a self-contained population. You've got one group of cells. With one treatment, you've got 12%, with one, you've got 80%. Okay? There's not a lot you can argue about with that. With a more complex population, however, it comes down to context, and context is provided by cell count. So on the Nova Express software, and on the Nova side, because it's a syringe-driven instrument, you actually get a parameter which is absolute count. So these E1 cells, there are 667 of those per microliter in the sample. So that's context. If you've got an instrument that doesn't have syringe-driven, and I wouldn't use the Akiri one, by the way, it's a plastic syringe, and variability is up to about 28%, which isn't very good. If you haven't got an instrument like this, you may need to use count tubes. So this is a tube with a predefined number of beads in. And when you run it, these beads come out up here somewhere. So you gate on them, and because you know how many have been run, and because you know you made the tube up to exactly 1 mil, and you've run it, you know how many beads there are per microliter, and you know how many microliters you run because of that, and you can calculate it back. It's a bit of a faff, and they're quite expensive, about £1.50 each. But if that's something you have to do, you have to do it. Whereas these ones are used to look at fluorescences, the amount of fluorescence. Mean should only ever be used for a linear scale. If you're doing DNA cell cycle analysis, you can use mean. Don't use mean otherwise. The problem with mean is it is heavily influenced by outliers. Okay, you've run 10,000 events through. Somehow 3 lumps of antibody from the very bottom of your antibody tube have gone through. Okay, your cells are averaging 50 fluorescents. These lumps of antibody are averaging 100,000 fluorescents. There's 100,000 of them. You've run 10,000 cells. Each of those adds 10 to your mean. So rather than your mean being 50, it's now 80. Oh, look, we've increased fluorescence quite a lot. You haven't. You've got 3 lumps of antibody. Mean will do that. Geometric mean is the logarithmic average. Don't ask me to go into the equation, it's far too late. But basically it weights it as per number. The geometric mean, in that case, would go from 50 to maybe 58. There's still an impact of the outliers, but it's not as great. The median is going to be 50 in either case, because 3 events is not going to drag the median away from its whatever number it is. The downside to that is that if you have a population that looks like that with a side population on it, the median won't really change whether the side population's there or not. Because it's not really affected by outliers, and the side population's outliers. But the geometric mean will. And so...
So can you use any of those though if you've got a bimodal population?
You can use either, yes, you can use either of these. Now people say, well, which one to use? Actually, a lot of it comes down to which instruments you learn to use your cytometry on. Geometric mean tends to be a Becton Dickinson stat. That's the one they teach people to use. This is the one Beckman tends to teach people to use. This is the default one for FlowJo. This is not there. It just comes down to the companies. My personal advice is pick one and stick with it. What you don't want to be doing is pick and choosing. If you are a superlative mathematician, if anyone is here, great, go for it. I'm not. So if you are a superlative mathematician and you know which is which and which one is best, go, fine. The downside of trying to pick and choose is, if 1 week you're on this one and 1 week you're on this one, there's every chance you pick the wrong one each time. And when you email me and say, oh, this week we've got 80, I said, but last week you got 20. Yeah, but last week I used median, now I'm using geometric mean. Whoa, hang on, what? You know, you're going to confuse yourself and everyone else. So pick one and stick with it. It won't always be perfect, but you've got consistency. And in that situation, I think that's probably more important. Things like CV is really used for QC. CV is a coefficient of variation. It's just the width of the peak. The wider the peak, the higher the CV, and you tend to use it when you're looking at QC. I'm going to show that one. So, how do we analyse our data? I can't tell you how to analyse your data, your experiment. What I would say is use your biological controls to check your analysis is correct. So set up your analysis template, put some biological positives into it. Do they give you a positive result? Put some biological negatives in, some experimental positives and negatives. They give you positives and negatives where appropriate. If they do, well then your data analysis is correct. It has to be, by definition. Okay? And just try and keep it simple is the real key for that. But as I say, when it comes to data analysis, if you want my help with anything, just drop me an email. That's not a problem. Any questions, or do you just want to get to the last one? Right, so last up then is data presentation. Those faces are grinning at me every time I close this.